Alrighty, this is YouTube Homework 3. Sorry if there's AC in the background. My dad's a little crazy about it. So anyway, here we are. So the first question. Here we have a block, and we're looking at it at 3 different points in time. So I'll just read directly off the page. A block initially at rest is given a quick push by hand. The block slides across the floor, gradually slows down, and comes to rest. So here we're supposed to draw free body diagrams at each instant. So in the initial instant, so free body diagrams, of course, with the forces in all directions. So in the initial position, we have, of course, our gravity, which is the force. Where's my pointer? Pointing downwards. Force by Earth, and then the normal force. So there's no movement in the Y direction, however. On the X direction, we have the force of the hand, pushing the block forward, but there is a friction force, which is why the block is still at rest. However, in the next moment, so of course in the first place, the net force is 0. And in the second picture, the block is currently slowing, so it is accelerating negatively. And the reason for that, we only have a friction force. So there is a net force in the opposite direction that the block is moving. And of course, there's a normal force and the force by gravity, which are equivalent. And then finally, our block is at rest. And the only forces acting on the block at this time are our normal force and the force on the block from Earth, or gravity. So here we go. Rank the magnitudes of all horizontal forces in the diagram for instant 1. So at instant 1, we have the force of the hand and friction force. Now here I stated the force brought to, or force on the block by the hand was greater. So my reason for that is at this instant there is no velocity because this is just v naught. However, we know once the hand pushes off the block, it is moving. So there is a factor of acceleration in here. So there is there is a net force in the positive direction. It's just at this very specific instant hasn't. The movement has not begun. However, it is there is a net force, and we're able to see that in the next couple pictures because we know the block has moved and it begins to slow down. So it did accelerate, and there's a net force here. Because it moved from its initial resting position, we know that the force by the hand. Oh, excuse me. Where are you? Sorry, there we go. Sorry about that. The force by the hand is greater than our friction force. So, question C. Are any of the forces that you drew for instant 1 missing from your diagram for instant 2? And here, the force of the hand is no longer interacting with the block. And you can see that in a couple ways. We know that the block is slowing down, and as a result, we have a net force in the negative direction. So if the hand was still there, the block would most likely be moving at a constant velocity or continuing to accelerate in the positive direction or to the right. Let's see. And are any of the forces that you drew for instant 1 missing from your diagram for instant 3? If so, for each force that's missing, explain how you knew to include the force in the first diagram but not the third. And in instant 3, we have neither the friction force or the force of the hand. And we know that because the block is just at rest, completely at rest. So there's no movement, there's nothing attempting to move it forward, and nothing, no friction force required to hold it in place. And so, of course, we can see that because we know there's no push by the hand, and the block does not need to slow down, so it's just at rest. Those forces are no longer a factor. All right, let's go to next page. Hopefully you can read this. Sorry, it came out a little small. So, question 1. As an elevator approaches its destination, its speed decreases. However, it continues to move downwards. How does the acceleration of crate A compare to that of crate B? Oh, I'm in the wrong order here. Let's move forward. I'll fix these when we get to it. Two crates, A and B, are in an elevator as shown. The mass of crate A is greater than the mass of crate B. The elevator moves downward at a constant speed. How does the acceleration of crate A compare to that of crate B? So the key word here is that the elevator is moving at a constant speed. Because of that, we know that neither of them have acceleration. They're both, the acceleration value is 0, therefore they are both equal. And here's our free body diagrams. So, starting with crate A, we have the gravity, so F of Earth acting on A, and then the normal force acting in the positive y direction, the force of box B on A. And then we have the free body diagram for crate B. So crate B is a little different. Because it's on the bottom, there is the downward force of A on B and the downward force of E on B. And then the normal force, which is equivalent to force of A on B plus the force of Earth on B. Of course, these are two normal forces. Rank the forces on the crates according to magnitude from largest to smallest. So I assume that our normal force acting in the positive y direction on B would be our greatest. My reasoning for that is that it was equivalent to the force of A on B and the force of E on B. And so it's basically the gravity of B and the gravity of A, and it's the normal force is equal to those two forces. After that, I had the force of B acting on A, and the force of B acting on A equals the force of gravity acting on A. And then I also had the force of A acting on B. So the force of A acting on B, I assumed, was going to be the same as Earth acting on A. It was just its mass being pushed in the downward direction. And then B acting on A, normal force, is equivalent to E acting on A, and that explains why there is no acceleration for box A. And then our final force is over here, Earth acting on B. We know that's the lowest because the mass of B is lower than A, so it cannot be equivalent to the force of Earth acting on A. It has to be less than. Alright, hopefully you can read this, but I'll try to explain. In these spaces provided at the right, draw arrows to indicate the direction of the net force on each crate. If the net force on either crate is 0, state so explicitly. So here I wrote, both net forces are 0. And we know that because the elevator up here, once again, is moving at a constant speed. If there was a net force, our boxes would be accelerating. Is the magnitude of the net force on crate A greater than, less than, or equal to that on crate B? Once again, the net forces, being the most important keyword, they are equal. Otherwise, they would be accelerating. Alrighty, last page. Alright, so as the elevator approaches its destination, its speed decreases. How does the acceleration of crate A compare to that of crate B? In this scenario, there is a net force greater than 0. And we know that F net is equal to mass times acceleration. And both of these blocks, just based off the picture, I thought it was safe to assume they had the same acceleration. Therefore, the box with the higher mass will have the higher net force, as its net force is proportional to mass. So acceleration is the same, but their forces are different. The force of A is greater. Didn't even have to answer that question here, but it's part of part 3. Anyway, so part 2. In the spaces provided below, draw and label separate free body diagrams for the crates in this case. So, similar to the last case, we have the normal force of B acting on A, the force of Earth acting on A. And here we have the normal force, which is Earth acting on B, and F of A acting on B, so pushing down, and then Earth acting on B, pushing down. However, in this direction, we know since it's slowing down, it's first of all moving downwards, so moving downwards. However, it is decelerating, so the upward force should be greater than the downward force. So, for example, this normal force is going to be greater than these two forces right here. So, rank the forces on the crates according to magnitude. So, once again, we're looking at our normal force as the greatest. And my reasoning for that is we have crate A on top of crate B. So it's the normal force has to counteract the weight of both A and B. It's greater than. The force acting against us is greater than both of those forces together. Then we have the force of, I thought it was going to be B acting on A. And the reason for that is that crate A is also decelerating. So it has to be slowing down. I don't think it becomes clear until we look at the later forces. It has to be greater than the force of Earth acting on A. Otherwise, crate A would be accelerating either in the negative y direction or it would be at a constant velocity. And Earth acting on A has to be greater than the force of Earth acting on B, because A has a higher mass, and force of A acting on B. Yes, and the force of A acting on B is, of course, just equal to force of Earth acting on B. So these two forces are equivalent. And the force of B acting on A has to be greater than Earth acting on A. These are actually like the same forces, essentially, as seen here. And then Earth acting on B is once again the lowest, and we know that because B's mass is lower than A's. Okay. And the spaces provided at the right. Draw arrows to indicate the direction of the net force on each crate. And here we know, since the boxes are both accelerating, we'll call it the positive direction because it's positive in the y. They are both accelerating the positive y direction. And basically the reasoning behind that is there's a net force in the positive direction. Is the magnitude of the net. Alright, the last question is the magnitude of the net force acting on crate A less than or equal to that on crate B? And we know that the net force acting on A has to be greater because the mass is greater. Their accelerations are equivalent, however, F net is proportional to their mass, and the mass of A is greater than B.